Welcome to video lecture F9. This one is on quadratic forms and the principal axes theorem. I'm your man with a plan, Tom Roby, and here's the plan. Quadratic forms generalize things like taking inner products of a vector with itself, and they come up in engineering applications involving optimization, signal processing, utility functions in economics, confidence ellipsoids in statistics, a variety of places that are actually real-life applications. So our goals are to analyze how a symmetric matrix A defines a quadratic form, and we'll actually define it that way, and then we'll leverage the orthogonal diagonalization of a matrix A as P dP transpose to compute a change of basis matrix P, that'll be the same P, which allows us to go back and forth between x coordinates and y coordinates. And with this change of variable, we'll actually be able to transform a quadratic form that's harder to understand into one that's more easily understood because it's given by a diagonal matrix, and that'll mean that it has no cross terms, and I'll explain what that means in a second. So here's the definition of a quadratic form. So quadratic form Q on r to the n is just a function from r to the n to r that's given by a symmetric matrix. It's x transpose AX. And that matrix is called the matrix of the quadratic form. Let me just give you an example right away so that you can see what's really going on. So if you have, say, the identity matrix, right, then what are you doing? So I have to multiply by x trans. This is a 2 by 2 matrix. So I take the transpose of my vector x1, x2, write it like this, right? And then I'm multiplying it by 1, 0, 0, 1. And then I'm multiplying it by the vector itself. So what happens when I do that? Well, multiplying by the identity doesn't do anything, right? So this is just x1, x2 as a row times x1, x2 as a column, and that's just x transpose times x. It's just the dot product, right? So this is just x1 squared plus x2 squared, or if you like, it's equal to x dotted with itself, the vector x dotted with itself. Okay? So that one's not hard to understand. What about another diagonal one where the entries aren't just 1, 1? Well, so let me just write that here. So if I have 3, 0, 0, negative 5, then when I multiply that by x1, x2, I'm just going to get 3 times x1 up above and minus 5x2 below. Okay, so when I take the dot product of that with this, I'll just end up getting 3x1 squared minus 5x2 squared. So if that algebra went a little bit fast, let's pause the video and double check that I did this right. But it's easy to remember because if I want the diagonal coefficients here, the diagonal entries here are the coefficients of the x squared, x1 squared, and x2 squared terms of these squared terms. Right, and so now you understand what a quadratic form really is. It's a way of taking the variables in your vector and making something that looks like a quadratic polynomial in it. These are nice quadratic polynomials in the sense that just x1 squared and x2 squared, but we'll see what happens with B as we get something that's a little bit more general. So if I think about, let's see. So if I take 7 minus 3 minus 3, 4, and I multiply that by x1, x2, then I just get the vector 7x1 minus 3x4 minus 3x1, sorry, x2 here, plus 4x2. All right, so I get something in terms of x1 and x2. And now I want to tack on to this, I want to add my x1, x2. So if I take x1, x2, and I multiply it by this column vector, so I'm really just taking the dot product of these two vectors. Then what do I get? Well, I end up getting x1 times 7x1 minus 3x2 plus x2 times minus 3x1 plus 4x2. And so that'll give me 7x1 squared, right? That'll be the x1 squared term. And now I'll have 4x2 squared And now what happens with the cross terms? Well, it looks like I get a minus 3x1, x2 here and a minus 3x1, x2 there. So I end up with a minus 6x1, x2. Okay? Let's just take a minute to analyze where these things come from. So the 7 and the 4 are clear in this matrix, right? But now let's think about what's the 6? Well, this 6 is really, if you think about this minus 3 and this minus 3, what's happening to them? Well, I've got the minus 3 here, the minus 3 here. So it shows up here and here. And then it combines, because x1, x2 is the same as x2, x1. They combine into a minus 6. And so that's what happens in general, right? If I've got a quadratic form and I've got, I know it's symmetric, and I've got, so minus 3, minus 3. If I had minus 2 and minus 2 here, then I get minus 4 there. It's always just double that. Okay, and finally, the matrix C, you could actually do this computation of x1c, x transpose c x, and you would get something. But the reason not to consider this kind of, this one's not symmetric, and in fact you would get the same answer as if you had replaced minus 3 and minus 5 with minus 4 and minus 4. So one of the reasons why we want it to be a symmetric matrix is that then we get a unique correspondence between the possible quadratic forms thought of as polynomials. So notice this is a polynomial where every term has degree 2, right? These are squared, and this is the product of two linear terms, so it also has degree 2. So that's another way of thinking about quadratic forms. All right, and so suppose I asked you, I gave you a quadratic form, and I said, let's go back now. Right? So the first thing you say is, well, okay, so this is clearly going from R3 to R, right? The output is just a single number when you plug in x1, x2, x3. So let's see. So in order to get the matrix A that corresponds to that, well, what do I need? So if you think about the analysis we just did, it looks like I'm going to want a minus 4 as the first diagonal entry, and a 7 as the second diagonal entry, and a minus 5 as the third diagonal entry. And now for the off-diagonal entries, what do? Well, I have a minus 6x1, x2, so that means I must have had a minus 3 in the 1, 2 entry and another minus 3 in the 2, 1 entry. I've got a 3x2, x3, so in the 2, 3 entry, which is this entry, I must have had half of that, so minus 3 halves here, and in the 3, 2 entry, 3, 2, right, so minus 3 halves here. Okay? And finally, there's no x1, x3, which means it's really 0, and so I'm splitting a 0 in half to get those two things, and there it is. That's the matrix that corresponds to this quadratic form. Okay? So this is a very straightforward correspondence. There's nothing very hard to understand about it. Just look at the quadratic terms, put those on the diagonal, and split all the cross terms in half, like that. Okay, so now I'd like you to recall how an invertible matrix, any invertible matrix, actually represents a change of basis from the standard coordinates to between the standard coordinates and the B coordinates, where B is the columns of the matrix P. Okay? And so let's just think about that. If x is equal to P times y, what that means is that if I have y written in B coordinates, then x is going to be written in ordinary coordinates. And the thing that's easy to get confused here is whether this should be a P or a P inverse, right? One of these is a P and one of these is a P inverse, because you're going back and forth between the two different sets of coordinates. But which is which is the question that can be confusing. And so it's always good to do a reality check. So here's the standard reality check I do. I look at this equation and I say, okay, y is supposed to be in B coordinates, right? So what if y were the vector 1, 0, 0, 0, 0, 0? What would that do? Well, if y is 1, 0, 0, 0, 0, when I apply P to it, when I apply P to that matrix, P to that column vector, that just pulls out the first column of P, right? Just by the, you could think of it either way, but maybe easiest is if you think about it as that vector, P times that vector, you're using that coordinates of those vectors as weights to give you the weight on the set of columns of P, right? So you're, say, taking the first column with weight 1 and the others with weight 0. All right? So that means that your output should be what your output is just the first column of P, of course, written in ordinary coordinates. And that's what this means, right? X written in ordinary coordinates is the same thing as Y written in as 1, 0, 0, 0, 0 written in B coordinates, which means just one copy of B, of the first column of P and nothing else. Okay, so that's, I don't know, maybe that reality check didn't help because I didn't write enough down. But that's the kind of reality check that's useful to do. And so here's the key idea, right? We can change variables to make our quadratic form simpler. How do we do that? Well, we already know that we know that we can always, if it's a symmetric matrix, which we always have here, that we can always take a real symmetric matrix and by change of basis, even an orthogonal change of basis, turn it into a diagonal matrix. But let's see where that would get us. Just saying, suppose we knew that we could rewrite, we had a change of variables where x was py. Well, then what would happen? X transpose ax would become py transpose apy. Now, when you transpose a product, you take the product of the transposes in the opposite order. So this becomes y transpose p transpose times a times py. And now group the p transpose ap together in the middle. And remember that if p is orthogonal, that's the same thing as p inverse ap. Right? So orthogonal matrices are the ones which are equal to their transpose. The inverse is equal to their transpose. And so I have p transpose ap. I can choose p's that makes this diagonal d. And so now, by this change of variables, I've converted a more complicated quadratic form that might have a bunch of cross terms in it to a simpler one which won't have any cross terms in it, all at a simple cost of changing variables. Okay, so you've probably seen already in various situations how changing variables can make your life easier. And I'll give you an example in the next segment that shows you how this works. Okay, before we switch to the next slide, I just wanted to show you a picture here that might help clarify the key idea on this slide. So the idea is that we start off with the lower picture. We've got some quadratic form. It's given by a matrix A. And so, for example, it might send x as an r to the n. Here, I'm just going to do an r squared example in red. So this takes r to the n to r, right, because that's what quadratic forms do. And what we're saying is that by changing our coordinates using this invertible matrix P, which means we can go, x equals py or y equals p inverse x, then, and the columns of that, the basis over the basis over here is the standard basis, and the basis over here is some new basis that we're constructing. So whenever we're given something with respect to a matrix A, we assume that that's the standard basis, and we do the change of basis thing, so that then we can review this matrix. We can rewrite the quadratic form with respect to that basis. And so what does that mean? That means that, for example, if x gets mapped to, say, 2x1 squared minus 4x1x2 plus 5x2 squared, this complicated quadratic form, we'll be able to rewrite it as y1, y2 just goes to 6y1 squared plus y2 squared. And this is clearly easier to understand than this one, as we'll see in some examples soon. Okay, so this is the picture to keep in mind. And I'm about to do this exact example and show you what's happening. Right, use a change of variables to simplify this matrix. Now, pretend you don't know this answer yet, because I'm about to show you how we got this answer. Right? You can just assume we started just knowing this and saying, OK, what's going to happen? All right, so just draw a line here so I don't write over myself. So what's the first step? The first step is what's the matrix A here that corresponds to this? All right, well, that's pretty easy, right? A is the matrix where I have a 2 on the 2 and 5 on the diagonal, and then split the minus 4 both ways. Okay, so step 1 is compute A is equal to 2 minus 2 minus 2, 5. Okay. All right, so then the next step is we want to diagonalize this, right? Now, the fact that this is a real symmetric matrix means that we can orthogonally diagonalize it. But to actually diagonalize it, first we need to find the eigenvalues. And so if you don't have any other way of doing it, then you take the characteristic polynomial, right? So if you compute chi of a, the characteristic polynomial, or chi a of lambda, it turns out to be something that factors as lambda minus 6 times lambda minus 1. So I'm skipping some details here, and maybe you want to actually pause the video and work that out for yourself. Compute a minus lambda I, the determinant of that, and show that when you get that quadratic polynomial that it factors as those two things. But that's all from previous video lectures, so I'll assume that you know how to do that. And I'll also assume that now you say, all right, well, so each of these, all of these eigenvalues are distinct, so they all correspond to linearly independent. And in fact, because this is a symmetric matrix, they correspond to orthogonal eigenvectors. So you just need to compute them, right? So you compute the null space of a minus 6i to get the eigenvector corresponding to this. And so you just follow the usual procedure. So lambda equals 6 corresponds to v1, which is 1 minus 2. And lambda equals 1 corresponds to v2, which is 2, 1. Okay. So again, I'm not showing you how I got this, but you can stop and do it now, or look at the outline of how this works and do it later, whatever you want. So now you remember that the eigenvectors are the columns of the change of basis matrix. All right, so therefore, P is going to be the matrix. Well, if I just put these things here, it would be 1, negative 2, 2, 1. But since I want the columns, I want them not just to be, notice those are orthogonal, but I actually want them to be orthonormal so that this is an orthogonal matrix. So that means I need to divide by the length of this matrix. Here I'm lucky in that both of these vectors have length square root of 5, so I just want to divide everything by the square root of 5. I probably could have just put 1 over the square root of 5 out in front of this matrix, and that would have been a little easier to read. But I just wanted to make sure you understand that these vectors are now orthonormal. They're each unit vectors, and their dot product is 0. And so this is a matrix whose inverse is its transpose, which makes computing its inverse super easy. OK. Good. So now what that says is that if with this P, we'll get A is equal to P d P transpose, which implies that D equals P transpose AP, right? So if I just multiply, remember P transpose is P inverse in this case, so I just multiply by P transpose on each side and P inverse on each side, and I'll get P transpose AP over here, and I'll get D by itself. And what is in fact this matrix D? We know what that is, right? Because it's the matrix of eigenvalues, right? So this is just going to be 6, 0, 0, 1. And the only thing you've really got to be careful about here is to make sure that you write these eigenvalues in the same order that they corresponded with those eigenvectors. OK. All right, so that's it, right? Really, I mean, now I can just say that I can rewrite Q as the quadratic form that takes a vector written in y coordinates, written with respect to this basis. 1 over the square root of 5 minus 2 over the square root of 5 is the first vector, and 2 over the square root of 5, 1 over the square root of 5 is the second vector. If I write y in terms of this basis, then my output is just 6 times y1 squared plus y2 squared, right? The coefficients of these vectors. And we could even make that more explicit, right? So what can I do? I can say, all right, so I think I've got plenty of space to write down at the bottom here. So y1, y2 is equal to P inverse times x1, x2, right? So if I'm given x1, x2, I can write it as P inverse times this. Okay, and so what's that? Well, that's the transpose of this matrix, right? So that's 1 over the square root of 5 minus 2 over the square root of 5, 2 over the square root of 5, 1 over the square root of 5 times x1, x2. And so that corresponds to a sequence of equations. I'm just going to, for once, let's go back to thinking about things in terms of equations. It's saying that I write the variable y1 as 1 over the square root of 5 times x1 minus 2 over the square root of 5 times x2. And y2 gets written as 2 over the square root of 5 x1 plus 1 over the square root of 5 x2. Okay? So that's the very specific concrete change of variables that all of this represents, right? And you can even do an example, right? So if you can check, for example, if so suppose that I look at q of 3, 1, right, in ordinary coordinates. Well, q of 3, 1 just means, okay, 2 times 3 squared minus 4 times 3 times 1 plus 5 times 1 squared. So what do I get? 18 plus 5 is 23 minus 12 is 11. Okay? On the other hand, if I think about q with respect to y coordinates, what should that be of? Well, now in terms of, so 3, 1 here becomes, I guess I've got to compute this now, right? So y1, y2 equals p inverse times 3, 1. And that's equal to, let me just pull this 1 out of the square root of 5 out of the whole matrix. 1 minus 2, 2, 1 times 3, 1. And so that'll just end up being 1 over the square root of 5 times 1, 7. Okay? So now if I apply qy to 1 over the square root of 5, 7 over the square root of 5, right? With respect to these coordinates, it's 6y1 squared plus y2 squared, right? So, okay, so I get 6 times 1 over the square root of 5 squared plus 7, plus 7 over the, plus 1 times 7 over the square root of 5 squared. Okay, so this be the 1 over square root of 5 squared just becomes 1/5, and I get 1/5 times 6 squared, which is 36, plus, oh, not 6 squared, just 6. 6 plus 7 squared, so that's 49 plus 6 is 55 divided by 5 is 11. Okay, so as amazing as it seems, right, I get the same output when I take my vector 3, 1 and plug it in here. If I represented it as I would represent it in terms of y coordinates, it would be 1 over the square root of 5, 7 over the square root of 5. I still get 11. Okay, so I haven't changed the quadratic form. I've just changed my point of view of how I think about a certain point in r to the n, what basis, the basis with respect to which I represent it. Okay? And so that's it, right? I've been able to take this quadratic form and write it as a simpler quadratic form. And the principal axes theorem just says I can always do this, right? So if I have any quadratic form on r to the n corresponding to a symmetric matrix, then I can find an orthogonal change of basis matrix P, x is equal to py, and it transforms my q of x equals x transpose ax to q of y equals y transpose dy, where d is diagonal, so there are no cross terms. Okay? We're going to use this several times later on, so it's important to understand what it means, and that's why I did this whole full-blown example, so that you could see how all the pieces fit together. And now the principal axes of the quadratic form, what are those? Well, those are just the columns of P, right? So the new axes, my old axes were 1, 0, 0, 1, and my new axes are 1 over the square root of 5 minus 2 over the square root of 5, 2 over the square root of 5, 1 over the square root of 5. So if you want to think about what that means is, instead of whenever you do an orthogonal transformation, you don't change distance and you don't change geometry. So if I take so that means that these guys are still unit vectors, right, as they are. And so if you think about, like, even in R3, if you apply an orthogonal transformation, all you're really doing is rotating it. 0 has to go to 0. So you're rotating things around. Maybe you're reflecting things. So maybe I need to put my left hand here now, right? So maybe I apply a reflection to it, and that would change it. But other than reflections and rotations, I'm just moving things around the space. I'm not stretching anything at all. Okay? So that's why you get quadratic forms and why they work well for optimization, because these matrices that we're translating things by won't change the length of unit vectors. Okay? So that's what's coming up in the next video lectures. We'll see soon how this theorem will be used to classify quadratic forms and how to handle optimization problems. But that's it for video lecture F9. Thank you very much for your kind attention.